Namaste bachcho and welcome. Today we are starting a very important topic from our current electricity unit, Ohm's law. Now don't worry, we are going to learn it in such a simple way that you'll never forget it, and it will be perfectly safe for your exams.
Okay, let's dive right in with a simple question you've probably seen at home. Have you ever wondered this? You have the same 230-volt socket, right? But it can power a huge 2,000-watt geyser, and at the same time, it can gently charge your tiny 20-watt phone charger. How does that work? Well, the answer lies in one simple rule we are going to master today.
To understand this, let's just forget about electricity for a minute. Seriously, just think about something much, much simpler. Water flowing in a pipe. Trust me, this little picture in your mind is going to make everything crystal clear.
So, first things first. For water to flow, we need something to push it, correct? You know, like a water pump or having a tank way up high on the roof. This push, this pressure, that is exactly like the voltage in a circuit. More pressure means a stronger push, right? So more voltage means a stronger electrical push.
Okay, so we have the push. Now, what about the actual amount of water that's flowing through that pipe every second? That's the flow. And in electricity, this flow is what we call the current. It makes perfect sense, no? The more push you have, which is the voltage, the more flow you're going to get, which is the current.
But what if the pipe is very, very narrow? Or maybe it has some stones or dirt inside, creating a blockage. What happens then? The flow of water will reduce, won't it? Even with the same amount of push. Well, this blockage is exactly what resistance is in a wire. It's the thing that tries to block the flow.
All right, now let's look at the official definition you need for your exams. It sounds a bit formal, but don't worry. It says that the current is directly proportional to the potential difference. Now, what's really interesting here is that potential difference is just the fancy scientific name for voltage, for the push we were just talking about. So this whole definition is just a formal way of saying what we already figured out with our water type. More push gives you more flow. Simple as that.
So the crucial point boils down to this simple formula. Voltage equals current times resistance. V equals IR. This is the heart of Ohm's law. You know, a good way to remember this is just say VIR. Kind of like the whir sound a fan makes, VIR. Lock that in your mind.
Okay, so let's quickly build the logic here. How did we get to this formula? Well, step one was Ohm's observation. He found that if you double the voltage, the push, the current, the flow also doubles. They're directly proportional. Then, to make it an equation, he needed a constant to connect them. He called that constant resistance, or R. And what is this resistance really? It's not electrons being lazy. It is the result of countless, and I mean countless, collisions that the moving electrons have with the atoms inside the wire. It's like a traffic jam.
Let's apply this with a very simple, non-scary example, okay? We have a resistor, a blockage of 100 ohms, and there's a voltage, a push of 10 volts across it. All we need to do is find the current.
So we just use our magic formula. I equals V divided by R. We put in the numbers. 10 volts divided by 100 ohms, and that gives us 0.1 amperes. See? It's that simple. Nothing to be afraid of.
Now, ध्यान से सुनो बच्चों. This is super important. This is where many students make silly mistakes in their exams and lose marks for no reason. Let's make sure you don't fall into these traps.
Okay, the first big mistake is thinking electrons are lazy, that they don't want to move, and that's why there's resistance. No, that's completely wrong. Electrons are incredibly active. They're buzzing around. Resistance is all about the traffic jam. It's about the constant collisions they have with the atoms in the wire.
And here's another classic trap. Many students look at I equals V by R, and they think, aha, if R is 0, then current must be infinite. But that's not how it works. That's a trap. It's a special case where Ohm's law itself tells you that if R is 0, then V must also be 0. This happens in special things called superconductors. The current can be very large, for sure, but it is always finite, limited by other parts of the circuit.
So the crucial point is, just lock this into your mind. Resistance is all about collisions. Just imagine you're trying to run through a really crowded hallway at school. All that bumping into people, that's resistance.
So why do we spend so much time on this one little law? I mean, why is it such a big deal? Because it's not just another formula. It's the foundation, it's the cornerstone for so many other important concepts in electricity.
I mean, it helps us understand everything, from calculating power and how hot a wire is going to get, to analyzing really complex circuits using something called Kirchhoff's rules later on.
It even helps us understand how fuses and circuit breakers protect our homes. It really is the key that unlocks the rest of the chapter.
Okay, before we finish up, here is a quick summary of everything you need for your exam. Think of this as your final checklist for full marks on this topic.
These are the absolute essentials. Point 1. The law is V equals IR. Voltage is proportional to current. Point 2. Resistance is the opposition to that current, and we measure it in ohms. Point 3. Resistance is caused by microscopic collisions, not laziness. And finally, point 4. This law is great for most metals, but it doesn't work for everything, like semiconductors. If you just remember these 4 points, you are in a very good position for any question on this.
And to leave you with a final thought, we've seen that Ohm's law is a brilliant rule for simple things like a wire. But what happens inside something really complex, like your phone's processor, where the materials are not so simple? Well, that's where this law has its limits. And that is what leads us to the super exciting world of semiconductors and electronics. We'll explore that next time. Well done today.